Yeah, we are recording. So let me just start with a question, which is a simpler version of the question we were doing last time. Okay, you'll see. So let f be a function here, which is from R to R. You could say differentiable and everything. It's differentiable. Actually, double differentiable. Differentiable. If we are told that limit extend to infinity, fx plus f double dash x. So this is a question I just framed, and I think this can help us to get fx plus f double dash x is equal to 0. Then does this imply that limit extending to infinity fx first of all exists? This is a much simpler question. So let's think about this first. Wait, have I shared that? Yeah, I've shared this. So last time we only had a single derivative here, but in fact this is easier, as I think. So let's think about this first. So what do you guys think? Do you think it is true? Maybe before even you prove, what is your guess? Because we did talk about this last time, means similar thing last time, and we did give some intuition as to how it could not be true. Okay, so just think about it. Meanwhile, just give me a minute. I just move to a quieter place. There's some noise here. So 1 minute. Okay, so anything? Hello, no one has. So no one has thought about this last time. Hello, am I audible? Yeah, yeah, I can't hear. Hello. Yes, yes. Okay, okay, good. That's okay. So yeah, so at least I know that. Okay. So last time we were wondering how this could fail, right? How could this fail? I mean, I could just tell you the answer also, but let me just say this was the idea I had in mind last time when I was saying that this may not be true. Well, I was saying it for single derivative, but for double derivative. How could this fail? Yeah, you can wonder about this. Now, it's very simple how this could fail. What could happen is that, I mean, what I mean is that this does not exist, right? So limit f, I'm just writing in short, does not exist. And then that implies that limit, so this is important, that if limit of f does not exist, then limit of f double dash also will not exist. Is that clear to everyone? Because of this equation, right? Sum of two limits, right? If one of them exists, if one of them doesn't exist, okay, then if this one exists, then the sum will never exist, right? That's some basic limit properties that you can try to prove. So this is the thing, right? Once you wonder how this could fail, it fails in a very precise way. But we know that limit of f plus f double dashed exists. So what does it mean, right? It means that the problem that is there in this first one and the problem in the second one, they sort of cancel out, right? So I'm trying to say that 1 and 2 cancel out. You see, the problems that are in 1 and in 2, they kind of cancel out in a very precise way because the limit is even 0. But even if this was some L, right, in some sense, the problems cancel out, right? But in this case, just the function can cancel out also. Okay. So if you take a very simple, if you think about the simplest, trivialist way in which it can cancel out is like this. Fx plus f double dash x itself being 0. Fx plus f double dash x itself being 0. Now, can you think of a function? Can you think of a function where this happens? Now, this is not difficult. Yeah, that's the first function you have to think that you'll think about. So when you see this kind of thing, well, you can think about that without all this thinking also. That's probably you would think about it directly. Yeah, so that's it. Sin x is the function, and now you get your answer. Now you get everything. Can anybody explain the rest of this? So now what? Yes, yes. So either both exist or none exist because the sum exists, because the limit of the sum exists. Right? So now we know that obviously sin x doesn't have a limit, right? As x goes to infinity, it doesn't have a unique limit. It's not badly behaved, but it doesn't have a unique limit, right? And that's your counter example. So does everybody see, right? Sin x satisfies this. So obviously this is true, but these things don't exist. Right? So basically I'm saying that this thing sin x does not exist. Does not exist. And we all of us know this. Now one could have thought about sine 1 by x also. If x was going to 0, then you may have maybe think about sine 1 by x. But those things you can do, I mean, that's you'll automatically get. Okay, so all of us see this is the exact idea I was saying, which was incorrect in the situation of first derivative, which we'll see that it's incorrect, but that's very, I think it is non-trivial to see. But in double derivative case, it is simple to see. Any doubts in this? It's a very, I think it's a very good counterexample type problem that I came up with a mistake of mine, beginning with a mistake. Yeah. Okay. Okay. So no questions here. All right. Okay. Now I want to, but what I want to do is give you guys a similar problem, which you should try for homework. Yeah. So let me just remove this. And then I'll come to the first derivative case. That's non-trivial. And that will show that our discussion of Lapidus rule was also incomplete. I would say, according to, I would say our standards, it was incomplete. I missed some very important thing. I'll say that, but let me give you a similar problem. So similar problem. So assume, okay, not assume, but assume f is a function from, let's be safe, this to this, this. 1 minute. Yeah, so this is not correct. I'll just make it positive. Or let me just make it, let me be very safe and make it like this. Okay. Such that limit of x going to infinity. And from here, we will eventually see a very general theorem. Okay, but right now we'll do this bits. You'll do it, and then we'll see that later. This situation. So this is similar and it's continuous. No. I shouldn't say continuous. 1 minute. So this is 2. And I will just say that continuous in, yeah, otherwise there's nothing to do, right? If I just say continuous. So at 0, we don't know. Okay. Other than that, it's continuous. Just that this happens, then does limit fx exist? Yeah. You can note this down. I'm giving it right now in the context so that you know it makes more sense rather than just giving it isolatedly. Yes, it is related to that. Yeah, it's related to that tightness of that thing. X plus 1 by x is 2 means x is 1 and so on. So, but yeah, think about it. Okay. So these are similar questions in the sense that you can see from an equation relating to f, or from a combination. Yeah, if its limit is given, then does the limit of f exist? Here we saw answer is no. Here we saw answer is yes. And now let's come to the real problem of today. Okay, here did I forget it? Try to think. Yeah, I'm being absent-minded. Okay, so yeah, note it down. And now we will come to the actual question. So what can we say in this case? That is the question.
In the second case, is it no?
In this one,
Yes.
in this one, I think the answer should be yes.
But if you take it as not 1 by x,
Fx equal to mod 1 by x. So one, no. So what? Mod 1 by x, obviously limit exists, right? No. But f is defined. F is defined at 0. See, mod 1 by x does not work, right? F has to be defined at 0. It may not be continuous there. It is not continuous there. Otherwise, it's done. Think about it. It's not such a trivial question. I had discussed this earlier with some other people. I think they are not here now. So yeah. Okay. Let's think about the first question. So I'm removing this. Let's think about this. So let me write just some equivalent statements. Here you have, okay. So here you have e to the power x fx by e to the power x. And that you can write it like this. And this is given. So this is 0, though that doesn't matter actually. This we already saw. So maybe this is not easy to think. Yeah, I don't think we can do this unless something more has to be said. This is, otherwise it becomes difficult. But let me just put it first in the language of Lapidus Rule. So what is the situation like? Yeah, situation is like given limit extend to infinity. Let's just use different notations. Fx prime by gx prime equal to 0, or I'll just say exist. This is given to us. But let us note the other things also. Limit extend to infinity, gx is infinity. So the denominator goes to infinity. The numerator we do not know. Just writing everything. Numerator meaning that the function, not the derivative function. This is don't know, because we don't know if e to the power x fx has a derivative or not. Okay. And now the question is that we are asking, right, is, now I'm abstracting it like this because without this, otherwise it's difficult to do this problem directly. Okay, not impossible, of course. I can just write the proof in this case, but yeah, it's difficult to see this in this clutter. So the question is, does a limit extend to infinity fx by gx exist? Yeah. So remember Lapidus rule. So we always understand Lapidus rule as a computational tool. We always think about it and we use it in probably hundreds of times. Right? Lapidus rule. So it's, well, this very big computational tool. Right? We use it to compute limits. But from the previous day's discussion, you can understand that more than a computational tool, it's a very deep limit proving tool, right? Proving limits. I'll say proving limits. And it's actually, this is a very somewhat deep. Using derivatives, using information about derivatives, it helps you to prove that some limits exist. And those are non-trivial ways, because simple epsilon delta arguments, whatever that means, will not work. Some mean value theorem type thing is needed. Or it can be another way, but yeah, one ways. This is the side of Lapidus rule which needs to be more appreciated. Okay. So the route I will take is I will try to mimic the proof of Lapidus rule, because see, Lapidus, in this thing, the conditions of the Lapidus rule are not satisfied, right? Co-conditions and we noticed it last time, and that's how we said that the answer is no, right? Lapidus rule is not satisfied, at least the Lapidus rule that we stated. Okay, but we can still try to copy the proof of Lapidus rule and see if we can, see if it works in this case. Okay, like condition is not satisfied doesn't mean the theorem will not hold, right? Condition being satisfied is a sufficient condition for Lapidus rule for, this thing implying this thing. That's sufficient. But we can still try to copy that method because that method is really unique in some sense using Cauchy mean value theorem, right? So let's just try to copy the technique and see. So that is the approach. So now I will, so is it, first of all, is it clear to everyone that this first question is, is just the same as this question? Same in a sense that if the answer to the second question is yes, then the answer to first question is yes. If the answer to the second question is yes, then we can surely say answer to the first one is also yes. The first one is a special case. But it's difficult to prove it like in this, or it will get messier also. And if we prove it in general, we'll also get a theorem. And in fact, that is the theorem that I should have said last time, but I missed. That's actually the Lapidus rule, which I kind of had forgotten. In fact, if you look at Rood in some good books, like Rood in advanced books, which is a little hard to penetrate, Rood is a little difficult to read in high school, depending on maturity. But there actually the full version is given. Yeah. See, one of the things here is that x is going to infinity. Okay. So remember, this is also there in our case. So that this is not actually very important. This is not actually very important. So see what you can do in this case. You can clearly remove. Sorry, you can clearly replace x with 1 by y, right? You can replace x with 1 by y. Replace x with 1 by y, and then everything becomes limit going to 0, right? So let's check that can be done. Okay. You can replace x with 1 by y, and then the function may not exist at 0, but its limit is the same as. If there is any doubt with this, you can say. I mean, this will become 1 by y, but then we can take this as our new gx or something, right? Some g1x. So everything around 0 doesn't make any difference, but maybe we are more comfortable with limits at 0, though it can be written, doesn't matter. So since all of us have seen the proof of Lapidus rule last time, can we try to use that, the method of the proof? So this g1 of y, yes, g1 of y, but I'm just calling that g of x. That's fine, right? It's just a new name I'm giving. Yeah, you see, yeah, I could write g1 of y, but then it doesn't really matter. X and y are just dummy variables. So yeah, it should be y going to 0. And yeah, you're right, it should be g1 of y. But then you can call this g and you can call y x. It doesn't matter everywhere. So that's why we're removing it. Yeah. So use the proof. Try to use the proof of. Yes. So you see, if I write g1 of x everywhere, Does anything change? No, I can just write, yeah, because it's true for all G1 kind. So you understand. This is what you do in integration, substitution, and so on, right, all the time.
So can we claim that limit x tends to infinity, e to the power x into f of x?
No, that was the problem. We cannot claim that, right? That was the real issue, because that's why I'll just go back, I'll come back. Because see here, conditions are not satisfied because we don't know this. This is a question mark, and which is exactly your question, right? Whether it's infinity or not. Yeah, so we don't know actually. Hold on, now what? Oh, it doesn't go forward after this. Is that, how can that happen? Oh, okay, so I have to remove. But usually it goes. Yeah. So we don't know anything about limit of f. Okay. So now we can think about it in this context only. Okay. Yeah. And then we can. So we can forget about the e to the power problem. That, let's just try to think, because it's cleaner, and you can. So nothing is told about limit of f. Okay. Nothing is told about limit of f. Yes, f is differentiable for all reals, but we don't know if its limit exists. So it could be sine x, for example. And also everywhere we are removing by 0. Not everywhere meaning that this limit is infinite that we're keeping. The definition of f dash x. Yeah, you can use that, but that means then you will be doing it from the very basics. What I'm trying to look at is using the proof of what we did last time, using Cauchy value theorem. I don't know if it will be so easy doing it from the very basics, but we can try. Because you see, you get a, simply thinking, you'll get a double limit and so on. H goes to 0, and then from here, how do you prove this? Not be so easy. But try to use the proof that we did last time. So last time we had something like this, right? Fx minus, okay, f0 was there, but someone had pointed out that you should maybe start with f of general. You can say f of a, but I'll just keep f of y. And then we had this. This is the thing where we started. So that this actually, the basic point is that if you just use this, then you're not using the fact that f is, okay, you're using it, but it's not directly, right? That f is differentiable, not at a point, but kind of globally differentiable, right? And so this would be f dashed. Yeah. So this would be what? This would be f dashed of c, maybe some c, we don't know. C, but remember that c is between c is between x and y, and everything is, you can take everything to be greater than 0, right? Because you can similarly do the negative one also, negative limit. Yeah, so this is kind of how we had tried to prove, but There we had both gy and fy had a same limit, but here we don't know if fy mean limit, meaning that we don't know limit of f. So we don't know limit of f. But remember, f is defined. Okay, f of y exists. All that is fine, right? f is defined in a neighborhood of 0. So if f and g are defined in a neighborhood of 0, -1 to 1, let's say. It will not be -1 to 1, but let's say -1 to 1 in a neighborhood of 0. Remember, we want to prove that limit of fx by gx exists as x goes to 0. We are doing limit at 0. No, limit at infinity may not exist, right? So yes. So see, this is the thing. Okay, before I go talk about this, so if f is from, let's say, R to R differentiable. Okay, why different? Just you can even take continuity case, but f is differentiable, or let's just take, no, let's keep this only differentiable from R to R. But this, you see, this is very different from asking the limit of this or of f dash x. This may not exist, right? So a function could be there from R to R. It could be differentiable, it could be anything. But limit when x goes to infinity, what does that mean? So that's something that we have to understand clearly. So what does limit at a point mean? If you have a point C, what does limit at that point mean? It means that the function kind of does not change much around the point C, right? It means that the function around the point C converges to some fixed value, doesn't change much, right? Fx minus L is very small around C, in a small enough neighborhood of C. Similarly, we know the definition, but now similarly for infinite case, this means that when x becomes very, very large, then f of x changes very, very less. Right, that's what it means, right? That's what it should mean. So you can take, for example, first I'll draw a picture. This is the first question that we had raised last time, that what is the meaning of this limit? That's very important to understand clearly, because it's not very properly defined in high school, I think. But let's say if you have a function like sine x, for example, right? So when x tends to infinity, where does sine x go? It should go, when we say where does it go, we are asking, does it go to some fixed number? And the answer is no, right? It doesn't go to any fixed number. It does not go to any fixed number, right? It kind of oscillates between 1 and -1. Okay, so that's okay. Now I want someone to properly define, I think, so we can just take a step back, properly define what this thing means. So we don't need differentiability or anything. What does this mean? So if you're told that this is a function from R to R, this we should do first. Function from R to R, let's say this L. What does this mean? For all x greater than k, mod of yes, yeah, right. That's fine. I mean, x has to be defined for all x bigger than k, right? So basically, we are saying that, so when we say this limit, we mean that this limit L will capture the behavior of the function as x becomes very large. Just like in the case of sequences, right? When n becomes very large. So if a number L captures the behavior, it means that f should be roughly like that. Okay, f is almost like that. So up to an error epsilon. So if you choose a point L and you want to say, non-mathematically that f is is like L, is more and more like L as x becomes very big. Right? What does that? How do you quantify that? You mean that okay, given any error. So it's just like sequences. Yeah. I mean, yeah, it can be defined completely in terms of sequences, but yeah, given any error, okay, given this error, you can go far enough, which means that you can find a k or a x naught. It's usually called xk, but it doesn't matter. You can find a k, not smallest k or anything, but just find a k, such that beyond this point, the function has to be inside this. So you can't really change much once you especially start reducing the epsilon, right? So it's like as f goes to infinity, the function is like a constant. And maybe all of you know this. This is also like saying that L is like a horizontal asymptote. Okay, that's another way in which it is said. L is like a horizontal asymptote. Like this line L, this function would kind of become almost like that. So that's a definition. Is the definition okay with you? Because this definition, because x goes to infinity, we kind of, yeah, we should know what that means. So let me do one thing, okay? Let me not create confusion, more confusion by making this 0. Let me keep this infinity only. Yeah, otherwise any more and more confusion will come, right? Though nothing is lost if I make it 0, but then you may not know if you've understood it correctly or not. Sometimes let's keep it as it is. Okay. So x is, let me just say x is bigger than y. That's all. And the c is in between, and there is no other condition because, going to infinity. Okay. So now the ground is set. We want to, yes, here, yes. Here I've used Cauchy mirror. And this is exactly what we did last time when we were doing the usual proof of the Lapidus rule, where condition on f was also given. That, for example, both limits are 0 and so on. But in this case, only one limit is infinite. The denominator of our function, its limit is infinite. How can we use that? Or is that enough? We'll try to. Okay. 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 How do we? Yeah, I mean, we have to do something because I cannot just directly take limit x goes to infinite. Right. Okay. So if that is the case, then how do we? Yeah. I mean, okay. But if you also just fix the y, and take limits on both sides, then what is wrong? So if y is fixed, and I try to take limit as x goes to infinity on both the sides. Then does that work? Right. Yeah. But you see, no, but yeah, think about this. Does everybody agree with this? C is here, X is here, Y is fixed. Now think, I'm fixing the Y and I'm letting, because this is the first instinct, right? So if I do this, then is it true that Cx goes to infinity? The subset argument is correct, but does Cx actually go to infinity? Should it have to go to infinity? That's a question mark. I mean, in natural good cases, it kind of should. Here stretching the X, this should maybe stretch also. But mathematics, a to the power x by x. No, but here G is not E. You're doing for a general thing. Let's do for a general thing. Yeah, maybe for that case you can do some arguments, but essentially it will be, this is simple and simpler. This is not harder than that. So and here we'll prove a general result. No, so the problem here is that this should not be difficult. This is just this question. If you just focus on this, I am letting the x go to infinity, but I'm fixing the y. And Cx is the mean that you get. Then should Cx go to infinity? Is it necessary? No. So what by mean, I mean that just applying the Cauchy mean value theorem, I'm taking 2 points, right? I'm taking 2 points x and y. X is bigger than y. Then I find the Cx, right? In between, for which the Cauchy mean value theorem equation holds. Now, if I'm increasing the x, does that imply the Cx should also increase? Does it have to go to infinity? Not just increase, but does it have to go to infinity? Y is fixed. But logically, is it mandatory? Yeah, geometrically it should. But if you just look at the condition, the only condition on Cx is that it should be less than y, x and bigger than y. Right? There is no mandate that it should go to infinity. Right? Which definition? No, but this doesn't have anything to do with that. So forget about the limit for a minute. Right? This is just, I have an x, I have a y. I mean, you can just think of it like this also, right? That this is 0 and let's say x was 1. Now you made x equal to 2. You made x equal to 3. The Cx will change, but is it mandatory the Cx will also increase? No, right? Exactly. The only condition the Cx has to satisfy is that it has to be between y and 3, y and 4, y and 5. So, yes, in fact, it can go reverse. Yeah, something. Yeah. Okay. So yeah, point is that it will it naturally it should go forward. If you just draw diagrams, you could see, maybe just take mean value theorem. You can take gx to be one identity function. You can take gx to value, and you can see that it should increase in good cases, but it's not necessary. Again, you can make a counter example. Maybe you can try to make. In fact, maybe put that as a homework. I'll write it after this problem. I'll write it clearly. But you see, without any condition, there's no, right? So that's fatal, right? If cx doesn't go to infinity, then how do you take the limit? I'll give the problem for homework. I'll write it, and then as Raghav said, so we'll discuss that also if that works. But for the time being, no, cx doesn't have to go to infinity. So let's finish this first. Right. But see, we want cx to go to infinity. So what should we do? Right. If you want to take y10 to infinity, then but then you cannot say, then can you say you want to fix the x, or what should you? Yes, exactly. Yeah. But then what do you do with x? That is the question. Hmm. That can create a little bit of issues. Let's see. Yeah, I mean x has to go to infinity. Uh, hmm. So if you're going to, yeah, x has to be, see, x has to be bigger than y. No doubt about that. But so first let us just write cy, or maybe I should not write cy, but anyways. Yeah, let me not write cy. It's in fact more confusing. Let's just keep it c. Now the problem is that if you take two limits now, then there is a problem, right? Because yes, that's in fact a problem. Yeah. So if, yeah, in fact it doesn't make much. So it makes sense, but it's a little difficult maybe. So if you say this, if you say this, then actually, see, this does not make sense. And same on that side, right side. This does not make too much sense, because this, if you want to read this formally, then this means firstly that you have to fix the x and take y to infinity. Right. So you have to fix some x, and if you take y to infinity, then for a different x, the y will again go to infinity. Okay. So before I define it, I'm just thinking if this makes sense. So 1 minute. If I fix a x and then I let y to infinity. Yeah. So what this means is that, look, this will be this answer of this limit. If this limit exists, right, it will be a function of x. Right. It will be, let's say, h of x. And then you're taking limit of that as x goes to infinity. So it actually gets a little complicated. Okay. And you cannot exchange the limits. So those are some critical things. But I don't want to go into that now. Okay. So essentially this becomes a two variable function, and first you're taking limit of x and then y. So no, I will not. I don't think we should do this. This will get a bit complicated. Yeah, so here, what do we do? I mean, if I just say, 1 minute. So if you just take y to infinity, the problem is that if you fix the x and then you take y to infinity, then again c will not necessarily go to infinity. Right? Is that right? If you fix the x, so if x is fixed, yeah. No, that doesn't imply that, right? C is a different thing, because if you fix the x and then you take y, increase the y, then eventually the y becomes bigger than x, and then again you have the same problem. Yeah, so the problem is all this is that you actually cannot just take limit on both sides like this. It means you can take, but it's not very useful in this situation. That is the message from here. Okay, and you also cannot say take limit x and y simultaneously. That also is not too good. Yeah, maybe that can be done. So there is a notion, but then that is not in our syllabus, in the sense that that needs a few more things to be said. You can take both tending to infinity. Okay, so that will be outside a ball of some radius, but let's not go into that. Then I think it will work, but we cannot do all that, right? We cannot do so much machinery now. So let's see what then we can do. So what we can do, yeah, just a little, yeah. Let me just try to, first at least let's try to bring this expression fx by gx in the picture. Okay, why I'm saying that, bringing fx by gx in the picture, because gx limit is infinite, right? So it may actually cancel a lot of other things. So let's try to bring fx by gx in the picture. How can we bring that? Like forcefully, just by algebra. So we can bring it. Can just bring gx here, then multiply, and maybe like this. So just on the left hand side, we are doing these things. And then we can again separate. So let me just write this. This is the same. It's equal to, there is no logic here. And this is this. So let me also do this thing. This is natural to do because, okay, and we know that this is f dash c by g dash c. Okay, so we already have our object of interest here. Okay, and we want to show that the limit exists. In fact, we want to show that the limit exists and the limit is equal to L, and we can use that to our advantage maybe. Yeah, so let's see if we can use that. So remember, this limit is L. So we want to show that this limit is L. Maybe that's easier to do. Then we can just use that maybe. both the limits. We want to show that both that. So we are assuming that the first limit is L, means f dash by g dash x. Sorry, yeah, this limit is L as x goes to infinity. Okay, and we want to show that limit of fx by gx is also L. Okay, problem is that I cannot just take limit x tends to infinity here. Or can I? Yeah, I cannot do that because then the c will not go to infinity. So I need to do something. So I need to simultaneously move x and y towards infinity, but I don't want to just say x comma y tending to infinity. Okay, because that's a two variable limit thing, and then that has to be defined and so on. Otherwise, the concept may not make sense. Yes. So the first thing is C. We are tempted to take limit x going to infinity on both the sides, right? But the problem with taking x, we have already seen that problem, right? See, when you write it in this form, then now if you take ignore the second term. No, yeah, that's the thing. Yeah, that's the thing. But if you, but you can be tempted to say fix the y and take x tends to infinity. Okay, something like that. Then what happens? You will say, okay, when y is fixed, x goes to infinity, this becomes 0 because y is fixed. Because y is fixed, this becomes 0. So you get your answer. You can say, look, you got your answer. But the problem is that if you fix the y, then the c doesn't go to infinity. Right? This is the problem we saw earlier, right? In this case, that is the only problem because other things are being taken care of because we have written it like that. Okay. So it's not this will not work. So we cannot just blindly take the limit. Yeah. So that's the thing. So then I don't know what we can do because then if I yeah, so then what we can do maybe is this. See, given an epsilon greater than 0, we can go to the definition. Given an epsilon greater than 0, okay, we know that 1 minute. Yeah, let me just think. So what I want to do is I want to say that I can I can arrange for a x large enough so that this kind of vanishes, and I can arrange for, and this also kind of becomes negligible. But I'm not allowed to fix the y. That's a bit strange. Yeah, let's just think about this. This is a bit delicate. This is actually very delicate. 1 minute. Content, no. Then no. I that will become, it will go in a very different way actually. So 1 minute. So if we are going to, if we fix the y, right? So if we fix the y, so the problem that is happening is that both the limits are, the limit is also being taken at infinity, and the limit of gx is also infinity. So that's why doing the reasoning becomes a little difficult. Yeah. So, but let's see. If for a minute, if you fix the y, and 1 second. So that's L, right? That limit is L. So it means that as x. So yeah. So maybe I can write this first. Okay, given epsilon greater than 0, there exists a t, okay, such that for all t, for all x, or not, for all something, some v, for all v bigger than t, I can say this, we can get started at least, that this is less than L plus epsilon. That's the meaning. That's the meaning of limit x tend to infinity, right? That, so it will not be c, I'm sorry, it will be t. That's the definition. That's the definition of limit, right? Because this limit is L, this f dash x by g dash x, because the limit is L, it means that if you basically take something bigger than L, that is just some L plus epsilon, then this f prime t by g prime t is less than that after, you know, when t becomes big enough beyond that point. So let's try to draw these things a little bit, not draw the whole picture, but just on the line, what is happening is that beyond this t, okay, beyond this t, this is what is happening. Now see, what would you like to show actually? You would like to show that the same thing happens for fx by gx also. Does everybody agree, right? We would like to show a similar thing for fx by gx also, right? Because we want to show the limit is L. Yeah, showing to the limit is L might be easier than just showing that it exists, because then you have something to work with, right? Okay, so let's write that. Let's write that because we want to show that. Let's make this more. No, this is actually a delicate proof, so it's okay to do this carefully. I mean, yeah. Okay. So yeah, so we eventually want, let's write it here so that we can use it to guide ourselves. We want, no, because I'm only looking at the upper limit now. Okay, I can say, so I can just say this, right? L minus epsilon. Okay, L plus epsilon and L minus epsilon, right? But I'm just focusing on L. Why won't it cross L? It will be in a small band around L. It can cross L, right? Yeah, but I'm not focusing on the minus epsilon part. It's already complicated. So if we can do this side, then we can arrange that also symmetric. We can take the maximum of the t's and so on. So yeah, what we want is ft by gt to be less than L plus epsilon for all t bigger than some, we don't know what, some w maybe. That will probably the same v will work. I don't know. Maybe not. I don't know. Actually, no. But how can we use this? We can use this to replace this equation by right. In what case? In the case when our x and y, I mean, if we choose our x and y to be bigger than v, then the c is also bigger than v. And so this will be less than epsilon, right? Because this was, so remember, if we just turn back, okay, it's already here at this one, right? F dash c by g dash c, this is what it's equal to. Okay, it's equal to f dash t by g dash c, and we know that because it tends to L, this will be less than L plus epsilon. So now we are working outside. So I made another mistake. For there exists a v here, right? There exists a v such that for all t bigger than that v, and this will be v, or yeah, okay. So this will be less than. So We have chosen a V and we are working beyond that now. We are working beyond the V, okay? And we know that for all points beyond this, f dash x by g dash x is less than L plus epsilon. So we have something to start with. Now we want to use this somehow to show that fx by gx is also less than L plus epsilon. So this is, so remember this is true for all x and y bigger than v. Is that okay? Everybody's okay with this? For all x and y bigger than v, this is true. For all x and y bigger than v. Any y, any x. Now what do we do? Now we can try to simplify, right? We can try to first of all maybe cross multiply or something, or yeah, maybe do some cross multiplication, right? Yeah, let's do that. Can I cross multiply? See, you guys obviously know to cross multiply, I need this thing to be positive. I need this thing to be positive, right? So this must be, so I need to ensure that gy by gx is less than 1. I need to ensure that. No, but g is not an increasing function, right? But we can still ensure this. That's the magic, right? We can ensure this because see, for every no, wait, what am I saying? Wait, 1 minute. So we want this to be positive. So we want this to be less than 1. And wait, y is bigger than x. Is that making sense? Yeah, so here I've taken y bigger than x, but just 1 minute. But the way I've done the calculations, yeah, so we have made some no, but that does not change anything. The ratio is the same. 1 minute. Sorry, which one? Yeah, so then what will happen? Or does it become that? Okay, so let me, okay, so let me do that. And everything else is same? No, but then it's the same thing, right? Oh, then it's the same thing, right? So, but let's do that because it's more convenient actually for me to have this like this. So you see, nothing actually changes. Right. What am I doing? So this one, so why do I need to change? I can, if I just take, if I just 1 minute, yeah, if I just take x and y like this, and y is bigger than x. Yeah, let me not confuse myself. Let me just write this only because if y is bigger than x, I should write like this. And then, yeah, then this should be like this. Okay. And then everything, though nothing changes. Yeah, nothing changes, but yeah, we'll just write like this. Yeah, so then we want to ensure. Yes, right. So then I want to ensure that this is bigger than 1, right? Now this is not difficult, right? For any x, right? For any x, so for any x, right, you get a gx. Now you can find a y such that gy is bigger than gx. Why? Yes, right. So basically you put gx as your bound, gx as your m, right? And eventually g of y, you can find a y bigger than that, which will actually cross gx, right? So this will actually be true for all y bigger than, you can find a y naught such that for all y bigger than y naught, actually this will be true. Okay, so basically I can always have such y's. Given any x, I can always find such a y. So I can do this. Right? Given any x, I can always find such a y such that this happens. Um, hmm, 1 minute. 2. No, but no, but then I want this to go to 0. That is the point. Oh God, we are just making some simple, symbolic errors here. And that's why everything is going wrong. Yeah, the y is bigger than x. So this actually cannot go to 0, right? But if the x was bigger than y, then this can be made to go to 0. And that's what I want. You see, I eventually want this to go to 0, right? Given a x, I want to, or given a y, I want to find the x. Oh, but then why is it less than? How is it coming like this? 1 minute. Oh, I got it. We are making a fundamental mistake. Yeah, this is, yeah, exactly. That's right. That's what I was saying. That's why everything is getting messed up, because see, it's very simple. No, but then that also doesn't work, right? Mm, what is happening? Okay, let's try that. Yeah, today brain is not working, I think. if we take it like this, then what happens? We get fy by gy and fx by gy, right? Yeah, so today a lot of silly mistakes are happening. So this is fy by gy and this becomes fx by gy, right? Okay, and this also changes. This becomes yes, right. Yeah, it becomes gx by gy, which is sort of what we want. So this becomes gx by gy. Now maybe I think I made a very big mistake earlier. I should have not done this division. I should have just cross multiplied simply, right? That would have been much better. Actually, yeah, let's scrap this and let's do that, because yeah, this is not a good thing. No, but I think we can, no, but that we are only using to say that this is positive or something like that, right? And that you could do just here also, right? Just make this positive using that. Yeah, so let's actually do that, because this actually creating unnecessary confusion, because it's not a conceptual confusion, it's a, I don't know, some problem, stupid confusion, calculation confusion. So yeah, let me remove this also, and let's remove this also. This yeah, let's remove this for the time being. Let's keep it simple. Yeah, so we know that for all t bigger than v, this holds. Okay, so then here we already have y is bigger than c. This is, we are assuming, is bigger than c is bigger than x, and now we are taking everything bigger than v also, because we want to use this thing. Okay, so now let's write the equation first before cross multiplying. So if I write the equation, this, there is no problem in writing this. Okay, now y is bigger than x. Okay, so for every x I can find a y such that gy minus gx is positive. Right? This we understand by, again, by the fact that it's going to infinity. Okay, for every, so it will not work for every x and y, but for every x you can find a y, and that's important. For every x can find a y such that gy minus gx is positive. Oh, but you are right. Then how would I bring that? Anyways, let's do it and then we'll worry about it later. Because yeah, then we can do this. Now again, I want to divide both sides. I want to divide both sides by what? Do I want to divide both sides by gy or by gx? What do people say? You want to divide by gx. I mean, you can try both the things and see one of them will work, but the point is that I want to divide both sides by gx because x has to, because eventually I want to take x to infinity, right? I want to take x to infinity eventually, in the sense that I want to make sure that x keeps increasing. Otherwise, this will not, c will not go to infinity. So yeah, so I'm dividing by, it's just, you can check. I mean, if this doesn't work, you will realize and you will, or maybe this will not work and we'll do the other thing. So we do this. So now maybe this is not so important. Remove this. Right. So this is what we have. So now if we simplify it, then what do we get? What do we get if we simplify? So the y is bigger than x. And let's see. So we get fy by gx. Oh, 1 second. There are only problems here. What is happening? Yeah, this is messed up. Yeah. So if we do, say, if I'm dividing by x, then for every x you can find a y such that gy minus gx is positive. So that's why I'm dividing by this x. No, that is not why I'm dividing by this. And by the way, you can ensure that g of x is positive, right? That is also clear because limit is, after some point it remains positive. So gx is positive can be ensured. Yeah, I'm now thinking of dividing by gy, not gx, because otherwise I will not get the. Let's see. Yeah, let's see. So fy, so we get fy by gy. Yeah, fy by gy, and here I get fx by gy, and here I get. Yeah, let me just write it in full. Gx by gy, and let me just put this on that side so that we can see clearly. Fx 1 minute. Yeah, something like that we have to do. No, so this is wrong. This was gy, right? No, this was gy, fx by gy. Yeah, right. So let me just arrange this thing, then let's see. Oh, okay. Yeah, so what you're saying, we ignore. How? Uh, mm, infinity. No, but if you, yeah, if one of them is fixed, then you can ignore. Otherwise, you can't ignore. 1 minute. So can I say that fx, I want to eventually say that this is less than something. Yeah, this is a little bit of a mess. So, why? Yeah, again, yeah, intuitively I can understand, but it's a little delicate, right? Intuitively I can understand, but mm, okay, so yeah, let's no, actually, I think what you're saying makes a lot of sense now. Yes, yes. Hmm. Mm-hmm. Uh, no, not just that. Yeah, so if x and y are close to each other, then what can we say? Then we can say this is one, right? Right. No, but something very fantastic has already happened here, which we didn't notice. You see, the c is gone from this now, right? We have taken the c to be big. So the point is that we have taken the c to be big enough, right? We took the c to be big enough so that uh, so that we have got inside that epsilon bound now. Okay, or you can just see that now there is no c here. Okay, see, because there is no c here, you can say that now you can say obviously fix x, because we want to take this limit, fix x and let y tend to infinity. Like, why can't we do this? Now there is no problem. Now the c doesn't need to go to infinity because we have taken c large enough already to get this epsilon. Do you guys see this, right? We have already taken c large enough so that it is bigger than the v. And so now we don't need it to go further extra. So you see, this problem is very delicate. We couldn't have directly shown the limit by taking limit on both sides. Okay, but we are showing that for every epsilon, we can make fy by gy less than L plus epsilon. Okay, so for that given epsilon, we have already chosen a big C and we are done away with C. Okay, we are done away with that C. Now we can take x, now we can fix the x and let y go to infinity. Now, what do I mean by fix the x, right? You fix the x, which, because some x works, right? There is some x we know which works, which makes this happen, right? So you take any x which is bigger than v, You find a y bigger than that, we know these things, right? If you take any x bigger than v, so any x bigger than v, find y naught. Okay, find a y naught, so that for all y bigger than y naught, this is true, and this we know we can arrange. So this is not just true for some y, remember. We can find a y naught such that this holds for all y bigger than y naught. That is important for all y, then only we can take y to infinity. Let's say the epsilon is fixed for the time being. Yes, it's arbitrary, but I'm trying to say that it is fixed. Right, it is fixed. Okay, for this fixed epsilon only, I can take limit y tend to infinity and x fixed. Right. So then what happens? So I'm doing this for one epsilon at a time. Though yes, as you say, it's arbitrary. We are doing it for an arbitrary epsilon, and that's why we are done. But the c will depend on the epsilon and everything. The v will depend on epsilon, obviously. You understand? So then it can become equality. But nonetheless, we will have this. You see, this actually becomes 0 because x is fixed. And similarly, this also becomes 0. That's the property of the limit. The limit of this will be less than e, but it could be equal. Remember, it could be equal. Okay. So I've said, so basically this means that the limit of fy by gy is less than equal to L plus epsilon. Okay. If you don't want to say like this for a second, you can also say like this. You can just say that, yeah, but no, let me not wait. So I'm just trying to say it in a slightly different way. We are already done, but one minute. Now, what I was trying to say, yeah, what I was trying to say is that you can say that for fix the x, okay, then there exists a y1 such that for all y bigger than y1, gx by gy is less than epsilon, and fx by gy is less than epsilon. You can manage these things, right? And then you actually get a more, maybe different way to see it. This becomes L plus epsilon minus epsilon times L plus epsilon plus epsilon, right? And I could have, in fact, instead of the epsilon, I could have chosen epsilon by L. And this, so I want a y1 such that this becomes less than epsilon by L, and you will see why. Because I want this whole thing to be less than L plus epsilon. Okay, epsilon by L, and this to be less than epsilon, or maybe epsilon by 4L or epsilon by 10. I can arrange all this for it. I can choose my epsilon and I can choose a y1 so that after that it works. So then the benefit of that is then I can just quickly write this by 10. Now you can check for yourself that this quantity is less than L plus epsilon. Assuming epsilon is less than 1. Okay, so what have I shown? I have shown that there is a y1 such that beyond that y1, fy by gy is less than L plus epsilon for any epsilon. So please ask if there are any questions so far. I mean, we are done. We are almost done. Slightly alternative, I'm not erasing this, but a slightly alternative way is to just take limits, quietly take limits and not worry too much. Okay, not be too rigorous. And it's, taking limits is not non-rigorous by any means, but then what you get is you get limit. I mean, actually, that is better. And in fact, that goes down to something like a squeeze in the end, because you will then end up showing that limit y tend to infinity, fy by gy is less than equal to L plus epsilon, right? And this will work for any, as I think you're saying, Adish was saying, I think, is that for any epsilon, this works, right? This works for any epsilon, because for different epsilons, you can get different C's and different V's and so on, but at the end, you can show this. You will get this, right? So this means that for all epsilon. Now, what does it mean? That this basically means that the limit is less than L, right? There's no other way, right? It has to be less than L because it's less than anything else, right? Less than equal to. So it's less than equal to L because it's true for all epsilon, right? You understand this. Now, symmetrically, you can run the same argument in L minus epsilon and do the same thing and probably get a little stuck at some places. Hopefully not like me. Okay, you can do these things better, faster. Okay, so the point is that this thing becomes bigger than L also in a similar way. And finally, we get that it's equal to L. Mm-hmm. Yes, okay, I will say that surely. Yeah. But is this clear to everyone? Okay, so this is different. Okay, this is different from taking limits on both the sides. And because of the C game, C is making so it's not so the problem here is not about, try to notice this, try to notice the small things. Problem is not about, and I think you should meditate, you should think over this. You should think over this again. Okay, whether you can want to watch it again or you want to just think on your own about this again and try to see a few glimpses and try to do it again on yourself. Okay, but think over this. You will observe these small things. Okay, it's not about x going to infinity. This was really not the problem. Okay, this was not the problem. Okay, because everywhere y bigger than y1 you can replace by a delta neighborhood such that in that all in that delta neighborhood. It was not the problem. That was not the problem. The problem was that we did not really have the limit of f. Okay, we didn't know that f also goes to the same limit. Otherwise, we could have done some 1 by f or something and worked it out. Because we did not know the limit of f, we kind of had to get rid of it. But it's also not so difficult because the G is kind of will use it up. Okay, but yeah, so that was the problem. Okay, but then that means that we have to maneuver both x and y. Usually we had to only worry about one of them, right? We could first deal with x altogether, then we worry about the y. But here we have to worry about them at the same time. Okay, so that's why we couldn't just take the limits. But yeah, that's probably not very useful. Just try to do this again on your own, or yeah, try to do it with minimal help on your own. Okay, this this statement is actually there in Rudin. Okay, but it's difficult to follow. You can read it. This is in Rudin. This is page number. I can share the screen and show you. Again, he does it in a slightly different way, but it's not very different. Oh yes, so it should be in partnership, because but does it have the full statement that only one has to go to infinity? Okay, then it's better. Uh, okay, that's good. Yeah, but yeah, that's perfect then. Yeah, because the earlier books, means the easier books like Spivak and all, they don't have it. Calculus books definitely, they say that both has to go to infinity or both have to go to 0. I think Wikipedia also says the same thing. Both has to go to infinity or both has to go to 0. But this other thing is there. It's in the analysis side. Now, the reason why it is there in the analysis books and not in the calculus books, because this proof is like analysis. You kind of need more things a little bit, right? That, yeah, we saw the, yeah. So this is the proof. This is the theorem, and he proves all the cases. And this other case is actually different. Okay. So he doesn't, I think, prove it for infinity. He just proves it for a point A. So it means extend, yeah. So A is there, and he is allowing it to be infinity. So he's allowing it to be a point and infinity at the same time because he has done some theory up before that, okay, which allows that. And basically, talk about infinity in the same way as you can talk about other numbers. Yeah, so then this is the case where gx goes to infinity as x goes to a. We did for x goes to infinity, so you can do for x goes to a also in the same way. This thing. And so if the limit of the ratio of the derivatives exists, and if gx goes to infinity, if both go to 0, it's fine. But if gx goes to infinity, then you don't need to care about f. The routine doesn't even say that. Bartle at least says that. Okay, that don't need. Otherwise, the student will be confused over what happened to f. But it doesn't matter. If you read the proof, and then he proves it. So this is point number 15. Using 15, his proof is slightly different. Okay. Yeah, maybe I kind of was referring to, because I'm not able to prove this on my own. I was getting stuck a little bit. Okay, it's kind of referring to this, but then I didn't read the full proof. Okay, then I had half of this in my mind and half we were trying to do in the class. And so I was getting, because the notations are different and we are doing it at infinity and so on, and the notations are completely different. So yeah, anyways, so you can use that or not. So now let's come to the two variable thing. Wait, so let me, okay, yeah. So yeah, so then the class is officially almost over. I'll just say the two variable function for 2 minutes and then leave. Okay, so this is what, okay. So if I just